Hello, today we're going to go over inverse functions. We're going to say what are inverse functions, and then we're going to say how can we tell if two functions are inverses to one another, okay? So if we look at this right here, what is an inverse function? There you go. What is an inverse function? In kind of a layman's type terms, we can say that two functions are inverses to one another if they undo one another. And we're going to see what that means here in a second. But there's a more technical definition we can get to here in a moment. And then, of course, we're going to see how can we tell if two are inverses to one another. So what do I mean by undoing one another? In the other video, we talked about saying a function must be one-to-one to say that they're inverses. We said that x squared is not one-to-one. And so we need to restrict its domain in order to get an inverse for it. So for instance, if I were to put y equals 3 squared, you'd say, okay, that equals 9. And then the square root of 9 equals 3. All right. But the problem with that is if I say y equals negative 3 squared, I also get 9. And so are we always going to take the positive root, the negative root? What's going on here? Because the square root of 9, technically, if you're looking at the negative value, if you say plus or minus, it could give us positive 3 or negative 3. And then this is no longer a function. So when I write it out like this, y equals square root of x, remember, unless I put a negative or a plus or minus in it, you can assume I want the principal root that's going to be positive. But in order for y equals x squared to have an inverse, it has to be one-to-one. So when we look at the graph of x squared, let me graph it here. What we need to do, there's x squared. Remember, it's not one-to-one because it doesn't pass the horizontal line test. So what we need to do is put in this restriction, and in Desmos, I'm going to write it like this. And notice what I'm doing is I'm cutting off the left half of the graph here. And all I'm doing is right here on Desmos, I'm telling it restrict the domain. Make x, only count the domain for x values of greater than or equal to 0. And now this function is one-to-one. And notice it will pass that horizontal line test. And its inverse, it can have an inverse now, is going to be the positive root of x. So graphed in blue there is its inverse. Now I want you to think about that for a moment because later we're going to start looking at these functions on the left here, and we're going to start talking about their graphs. So let's go back to this right here. So these are examples of inverses after we restrict the domain. Sometimes we have to do that, especially when we get into trigonometry. Let's look at another way we can approach these. So how do we know if they are inverses to one another? And that's where we're going to use the composition of functions. So here's my two functions. The f of x equals x minus 9 over 4, and the g of x equals 4x plus 9. And a typical problem I might ask you is show that they are inverses to one another. Now let me make a special note here. I'm not saying to find the inverse. That might have been something you learned in Algebra 2 where you switch the x and the y, solve for y, and yes, you do come up with the inverse. But in this case, I want you to just show using composition of functions. There is a difference. In the next lesson, we will talk about how to come up with the inverse of a function. But for right now, I want you to use composition of functions to show that two functions are inverses to one another. So remember how we did this. We're going to say the f of x, write it out, and everywhere I see an x, I'm going to put a set of parentheses. So this is the f of x right here, written out with the parentheses replacing the x. And then inside of that parentheses, I'm going to put the g of x. And now I can simplify this thing. So I've got 4x plus 9. The parentheses no longer matter in this situation. But I have plus 9 and a minus 9. They cancel out. And that leaves me with 4x over 4. And then from there, notice that 4 divided by 4 is 1. These go away, and I'm left with just x. Okay? So I'm telling you right off the bat, these are inverses to one another. For instance, if I have, let's do this. Let's find the f of, say, 12. What happens when you put in the f of 12? Well, go back up to this. It's 12 minus 9 over 4, which gives me 3/4. So the f of 12 equals 3/4. Now I want you to find the g of this output here, 3/4. So that gives me 4 times 3/4, because it's 4x plus 9 up here. And then I'm going to add 9 to it. Notice that the 4s, you multiply those out, you end up with just 3 plus 9, which equals 12. And this is what I mean when I said that small definition is that they undo one another. When I put 12 into this function, out pops 3/4. When I put 3/4 into the g function, it takes me back to what I originally put into the f function, 12 there. Just like when we had x squared a moment ago. When I look at this, when I put 3 into this function, if we just count just the positive values here, out pops a 9. When I put 9 into this function, it spits back out a 3. It takes me back to the beginning, all right, whatever I originally put in. And that's why this right here works out. They undo one another. So this is what's going on here. It's saying put x into the g function, and the g of x actually stands for a y value on this g function here. You take that y value and put it into the f function, and it should take you back to what you originally put into the g, which is x. So here's the key with composition functions. When I ask you to say, show that the two functions are inverses to one another, I want you to take the f of g of x, or whatever two functions, whatever we're calling them. You can likewise say the g of f of x, like I've got written right here. So let's try doing it that way. So if you use the g of f of x, let's write out the g function. That is going to be 4 times something plus 9. And inside of that parentheses, I'm going to put the f function, which is x minus 9 over 4. Now you just do your algebra here. 4 and 4 right here, they cancel each other out. And I get x minus 9 plus 9. And then these two knock each other out, and you're left with just x. So the g of f of x equals x. That's how we know they're inverses to one another. When you take the composition of the functions, you should just get x. So the f of g of x equals x, or the g of f of x will also equal x. Let's look at them graphically now. So if we switch over to our graphs in Desmos, I'm going to turn off these two functions. And there's the function we just had. And there's the inverse. So I want you to start looking for a pattern here in the graphs and see if you can tell by the end of the video what's going on. You know, there's a way that we can tell if two functions are inverses to one another graphically. So we have these two right here that we said were inverses. And then remember our original two were restricted. This one, those two right there are inverses. We're going to keep going through these functions, and then I'll give you the answer here in a moment. So let's look at our next example. We have negative 2/7 x minus 3. Let's find it there. There we go. And we've got negative 2x plus 6 over 7. I want to see, are these inverses or not? So I'm going to try with the f of g of x. So I'm going to write out the f function. And everywhere I see an x, I'm going to put a set of parentheses. And then inside the parentheses, put that g function. So negative 2x plus 6 over 7. This is how we show two functions are inverses to one another. So now we get the fun time of multiplying all this out and seeing if we get just x. So when I multiply negative 2 times negative 2, I get negative 4x. Negative 2 times 6 is 12. Remember, when we multiply, sorry, it's negative 12. When we multiply fractions, we multiply straight across, right? 7 times 7 is 49. And I got minus 3 right here. If you want to take this further, you could say, well, this is like saying over 1 and multiply both here by 49. But this is not going to work out to be inverses. We can check it graphically here. So look at the graph on these two. These don't show up. These don't give me f of x equals x, or the f of g of x equals x. Let's look at it graphically. I've got this one here, and then 2x, negative 2x plus 7. It actually gives me two parallel lines, doesn't it? or at least they appear to be parallel. I haven't, yeah, it should be parallel because they both have a slope of -2/7. So these are what two functions look like when they're not inverses. Now, don't get confused here. Just coincidentally, they're parallel. You can have lots of functions that are not inverses to one another that are not parallel lines. So I just want to give you one example of showing what happens when we're doing this math and it doesn't work out to be the f of x, the f of g of x not equaling x, then you don't have inverses. That's what happens. Let's look at another example. So on this one, we've got the f of x equals x cubed plus 5, and the g of x equals the cubic root of x minus 5. So once again, we're going to take the f of g of x. So I'm going to write out everywhere I see an x, I'm going to put a set of parentheses here. And so I get something cubed plus 5, and then inside the parentheses, I'm going to put the cubic root of x minus 5, cubic root there. Now, cubic root and cube cancel each other out. Why? Because they are inverses to one another. And then I end up with x minus 5 plus 5. Well, subtracting 5 and adding 5 will cancel out. And I'm left with the f of g of x equals x. So yes, they are inverses to one another. You don't have to do it both ways, but I'm just going to show you one more here using those two functions. First, find the g of x, write it out, and everywhere I see an x, put a set of parentheses. So that's the g function. And inside that parentheses, I'm going to put the f function. So let's write the f function in there. I got x cubed plus 5. Now, do some algebra here. Plus 5 and minus 5, they cancel out, and I get the cubic root of x cubed. And then these two right here will knock each other out, and I'm left with just x again. So the g of f of x. I'm just wanting to show you, it doesn't matter which way you take it, whichever way you see is easiest in the beginning, do it that way. You don't have to do it twice. I'm just giving you some examples here. Let's switch over to Desmos and take a look at it. So that's where we left off. Let's look at, turn off these two right here. So we have, there's our x cubed plus 5. It is the cubic function, shifted up 5. And then there's our cubic root function. Hopefully you're starting to see some patterns here. Let's click this one back on, our x squared and square root of x. Maybe not. You're seeing a little bit of symmetry there. So that's your big clue. Let's look at one more example. Actually, I've got a couple examples here. Let's see. But let's look at this one right here. So we've got the square root of x minus 4 and x squared plus 4. Notice that I am restricting the domain again because we got this x squared function going on. So we have to restrict the domain again, or we don't have a one-to-one function. We can't do inverses. So I'm going to take the f of g of x here. So write out the f function. Everywhere you see an x, put a set of parentheses. And then inside that parentheses, we're going to substitute x squared plus 4. This is kind of like the last one, except for it's square and square root instead of cube and cube root. The 4 and the minus 4, they knock each other out. And then that gives me the square root of x squared, which is just x. So the f of g of x equals x. That means they are inverses to one another. Okay? Now, I want you to see this on a table, because I could give you a table and say, are these two functions inverses? They're the ones we just did right here. So here's my x values, and this, I'm going to write these in. The 4 minus 4 is 0, square root of that is 0. 5 minus 4 is 1, square root of that is 1. 8 minus 4 is 4, square root of that is 2. 13 minus 4 is 9, square root of that is 3. Now, those are my outputs for those x values there. I chose those on purpose because they worked out to be pretty numbers. Now, I'm going to take that same set and put them in here. Those outputs I'm going to put into the input over here. This should say, actually, the g of x right there. That's the g function. So I'm going to put them into the g function. And so let's see, 0 squared plus 4 is 4. And then 1 squared plus 4 is 5. 2 squared plus 4 is 8. And 3 squared plus 4 is 13. So I want you to notice something. These are my inputs to the f of x. And notice they become my outputs on the g of x. Likewise, my inputs on the g of x become the outputs on the f of x. That's because they're inverses. They undo one another, right? And that's what's happening when we say the f of g of x equals x. It takes you back to the beginning, which you originally put in. Let's look over on Desmos and see what we got on our graphs here. So I've got that graphed right here. So there's your square root of x minus 4. There it is up there. And then we've got one more we're getting ready to do. That's the, well, x minus 5 and x plus 5. You can't really, they look like that. They're parallel to one another, but that's okay. They're still inverses. They still undo one another. And so the key here is this. They are symmetrical about the line, if you couldn't tell before, y equals x. So that line right there, I'm going to make it a dashed line. Let's see if we can do that. There it is, dashed line. And let's kind of clean this up a little bit. Let's cut off everything except for maybe one example. That way you can kind of see what's going on. So notice if I fold on that dashed line, these two will match up. So they are inverses to one another. And then if we look at the other set, let's look at another. Let's see, where's our other ones? Let's look at the cubic ones because they look nice, don't they? Notice if I fold that one on the line y equals x, they match up. That's the key. If I give you two graphs and I say, tell me if these are inverses or not, say, well, are they symmetrical over the line y equals x? If they are, then they're inverses. So as we're looking at this, we can see that inverses can be found algebraically using composition of functions like up here. They can be found using tables. So we can use tables to see if we have two functions that are inverses. And then of course we can look at the graph and say, are they symmetrical over y equals x? If they are, then we can say they're inverses there, okay? So that's what I want you to keep in mind as you go through these. You should be able to look at it through a table, you should be able to look at it through a graph, and you should be able to look at it algebraically using the composition of functions. Now in another lesson, I will give you a function and say, tell me what its inverse is. That's what you did in Algebra 2 where you switch the x's and y's and solve them. I get so many students on my quizzes when I say verify using composition of functions that the two are inverses, and they don't do what we did today. They actually take one function and find its inverse and show it that way. That's not what I'm looking for. That will get you points taken off. So please pay attention to the directions in the work I give you. If I say verify using composition of functions, I want you to take the f of g of x or the g of f of x. And then of course, be prepared to show me with using graphs and tables if two functions are inverses to one another. If you have any questions, let me know, and I'll be happy to help you. Thanks for watching.